Okay, so now that I've established the simple idea of an antiderivative, just a function whose derivative equals the one that you started with, let's examine this idea of the idea that the antiderivative is not unique, that there could be more than one different antiderivative. So far, here's what we've learned. If you have a function capital F whose derivative is lowercase f, and if you take another function, let's call it g, and define that as being capital F of x plus a constant, some constant c, doesn't matter what constant, it could be any constant, then what we know for sure is that the derivative of g is also going to equal lowercase f, right? Because the derivative of g prime here would be f prime plus 0, and capital F prime equals lowercase f. So what this is saying, in other words, is that if capital F is an antiderivative of lowercase f, then so is capital F of x plus a constant, right? That means that if you have one antiderivative, you actually have infinitely many different antiderivatives, because you could alter it by adding any constant you want. But the question remains, is that all you can do to get another antiderivative, or is it possible that there could exist some antiderivative for a function which looks completely different than the one you found? Like they're different from one another, not just by the addition of a constant, but rather in some more fundamental way. That is a good question to ask, and it turns out the answer is no. So the next theorem we're going to look at here establishes this idea, and we're going to look at a short sort of proof, like partial proof of this theorem. It says that if capital F is an antiderivative of lowercase f, then another function, capital G, can only be an antiderivative for f if, and it will be an antiderivative if, it is equal to the capital F plus a constant. Okay, so it has this g of x is another antiderivative of f if and only if capital G of x is equal to capital F of x plus a constant for some constant c. So this is establishing that yes, every time you add a constant, you're going to get another antiderivative, and also every other antiderivative can be achieved by just adding a constant to the one you already found. This gives us this idea of the set of all antiderivative functions for a given function, starting function. The set of all antiderivative functions are basically like, they're all different from one another by just the addition of a constant. That's it. There's no way that they could be more different from one another than just by being different by a constant. Like there's never going to be two antiderivatives that are fundamentally different, like they're different types of functions or something like that, or that they differ by some term other than just a constant term. So let's do a quick proof of this. Part of the proof here is already obvious, that, you know, if you differentiate something like this g of x equals f plus c, you get f prime plus 0. So obviously that's going to be a derivative. The part that we want to prove is that there's nothing else that could possibly be a derivative. So we're going to start by assuming, assume that capital F and capital G are both antiderivatives of lowercase f. Let's assume that. Now what we want to show is that capital F and capital G must be different from one another only by a constant. Okay? And so what are we going to do? We're going to look at the difference between them. G of x minus f of x. Capital G minus capital F. Okay, let's look at that difference. What happens if we take the derivative of that difference? The derivative with respect to x of capital G minus capital F. Well, we know that the derivative operator is going to distribute over this subtraction. So we're going to get the derivative of g minus the derivative of f. It'll look like this, g prime minus f prime. But since both g and f are antiderivatives for lowercase f, this is going to be lowercase f minus itself, right? Both of those derivatives are equal to the same thing. So this is 0, right? Now, one of the things that we know is that capital F and capital G are both differentiable, right, because they're antiderivatives of lowercase f. So if they're differentiable, they have to be continuous. Let's assume that they're continuous, and then we can make this conclusion. The only continuous function, I'll put an S on the end of that. The only continuous functions whose derivative is 0 are constant functions. All right, so that's a bit of a broad claim. All right, I'm not like providing all the proof for that. I'm not going into the really nitty-gritty details. But think back to what you've seen. If the derivative is constant, if the derivative is 0, it's a constant function. Like the derivative of a constant function is 0. We know that, right? And have you ever seen another function whose derivative is 0? No, you haven't. Only constant functions. The only other possibility would be like step functions, but those are not continuous. So we're kind of assuming continuity at the moment. So what this means is this means that, I'll write it like this. Therefore, our difference that we were looking at, g of x minus f of x, must be constant. If its derivative is 0, it must be constant. So then g of x equals f of x plus c. Like that. And that's basically it. So that kind of establishes, that pretty much sums up the explanation for why antiderivatives differ from one another only by the addition of a constant. This gives us something we call the general antiderivative. And the general antiderivative of a function lowercase f is capital F of x plus a constant, an arbitrary constant. So that's where capital F is just an antiderivative. Doesn't matter which one, really. We try to find just the simplest possible antiderivative. So capital F is an antiderivative of lowercase f. And then c, we usually use capital C here, is an arbitrary constant. And what that means is that we're rarely ever going to actually specify the value of c. Not if we're trying to find the general antiderivative. C will just be some unspecified constant that you just write at the end of the function. So we're going to find an antiderivative, and then we're going to write plus c on the end. And that indicates that you could add any constant you want and still have an antiderivative. Okay, we're going to go over more examples next.